Bismillahirrahmanirrahim. Today, inshallah, we shall complete all the important topics in this chapter, and after this, I'd like to elaborate on some other things. But the last of the important topics that we need to complete is a continuation of our exploration of complex numbers, how that relates to vectors, and how they are used in circuit diagram and circuit sciences. So this is a bit of a topic, but I don't believe it's particularly difficult. Now, if you recall, a complex number can be written as a combination of a real component and an imaginary component, a plus bi. Sometimes complex numbers are like, if for example z is a complex number, so z is this, and you could say maybe there's another complex number, z2 is being z1 is some other complex number, c plus di, etc. So for convenience sake, they can be given names like that. Previously also we explored the complex plane, where you apply complex numbers, and this is the real axis and this was the imaginary axis over here. So a complex number such as 3 plus 4i would be would not be represented by an ordered pair, but rather by a point at this location, 3 being the real component right here, and 4i being the imaginary component. So that point here, let's just say that is z, okay? So that is 3 plus 4i right there. Okay? Now, one thing we have to complete in regards to this is the definition of absolute value of a complex number. So in the real world, we had in real numbers world, absolute value of 3 was 3, absolute value of negative 3 was 3. But if I asked you what's the definition of an absolute value, and I have full confidence in you would have suggested that absolute value is the distance of the number from the origin or from 0. So absolute value is basically the distance of the number from 0. Now, if we apply the same analogy to complex numbers, the absolute value of a complex number like this would be the distance of that complex number from 0 or the origin like this. So I kind of overdid that over there. So that would be the absolute value of this complex number. Okay, so this would be the absolute value of z. Specifically, absolute value is the distance of this complex number from the origin. Now, then you understand that the complex number is a composite of a real component and an imaginary component, b. And as you can see over here, they form a little right triangle. Therefore, absolute value of z is going to be basically from the Pythagorean theorem. It's going to be a squared plus b squared and the square root of that, because as you recall from Pythagorean theorem, hardly you can forget, because I keep reminding you, a squared plus b squared equals c squared, from where a and b are the legs of the right triangle, c being the hypotenuse. So one thing that we have to appreciate is that the absolute value of a complex number is this. Okay, that's how you define absolute value of a complex number. Okay. Okay, so Bismillahirrahmanirrahim. So this is the absolute value. It's one thing we have to find. So then you also appreciate the second concept. So let me reiterate this. Absolute value of a complex number is a squared plus b squared and the square root of a squared plus b squared. It's the distance of that point from the origin. It's a point. Remember, complex number is a point. So that's the definition of absolute value of a complex number. The second topic of the day is that you recognize that complex numbers can be very useful as vector sciences. Okay, for example, if I have 1, 2, 3, 1, 2. So if I have this complex number, which is 3 plus 2i over here, And if you can imagine a vector, just if you can imagine a vector here, I meant to make it red, like this, okay. Then if you imagine another complex number such as 2 and 2 right over here, that's 2 plus 2i. And if you can imagine this vector over here, okay. Vectors, if you recall, are segments in a particular direction. So, and if you were to add these two complex numbers, that is 3 plus 2i, okay, plus 2 plus 2i, okay, if you were to add them, you would add the real component 5 plus 4i, correct? That would be over here, okay? Now, this is 5 plus 4i. Now, you recognize that if you were to use them as vectors, you would have one vector over here, all right? And if you were to put this second vector over here on top of this first vector, it would be like this. This because this is 2 and this is 2, okay? So basically, I took this vector from here and put it right over there. And the composite vector over here, from here to here, is just the addition of those two. So in other words, I did this, that's the original vector, and I just moved over the second vector over here, which was like this, okay? And then I got the composite vector, which was from here to here. So you can see that complex numbers can be used as vectors, and addition and subtraction of these vectors very conveniently, because they have two components. Vectors have an x and a component and a y component, so to speak. In this case, a real component and an imaginary component. Okay, so complex numbers can be used as vectors, and this is exploited in circuit mathematics. Okay, so I shall explore to you, I shall share with you what I know of circuits, which is not a whole lot, but I tell you the rudimentary knowledge of circuits. Now, a circuit, like when you plug a hairdryer toaster in the wall, that completes the circuit, right? Has to have a source of a power source, okay? And this is a symbol for battery, okay? This is a symbol for battery, and this is a symbol for alternating current source, okay? So this is a battery. So there's some symbols that first we have to learn. So this is a symbol for a battery. All right, a circuit is basically a highway for electrons. Okay, it's a highway. If you complete the circuit, and the electrons, they travel. They like to go from here or whatever, and then go across and go to the other side of the battery. So a circuit is a highway for electrons, and you use this highway to do work. So you can put, for example, a light bulb over there, because a light bulb, when the electrons go through the light bulb shines, right? So I'm just going to draw a light bulb over here. This is going to be like a pretend light bulb. This is not how you draw light bulbs in a circuit, but we're going to make it simplistic here. So that's a light bulb. So electrons flow through the light bulb and it shines, okay? But a circuit is not like this. If it had a circuit battery and going to a light bulb, light bulb will go boom, because it can't handle all those electrons at one time. It will burst. So you put other stuff in the circuit to cause certain resistance to flow of the current. Okay, so there are three terms that we must learn. The first is that frequently in a circuit you would put a resistor. Okay, a resistor. So I'm going to draw a resistor. A resistor is like this, kind of like a mountain. I didn't do a very good job there. Okay, so it's like that. I still didn't do a very good job here, but perhaps you can do better. That's cool. Okay, that is a resistor. Okay, the concept of resistance to flow current is like this. Okay, different things can resist the flow of current. For example, would you use a ice skate, for example? Here's an ice skate. Pretty cool ice looking. Ooh, okay. Would you use ice skating boots on a cement walkway? No. No, you won't, because there's too much resistance, right? So there's a certain resistance to just ice skating. You know, you'd be kind of silly with that, but you know, ice skating on the cement with the ice skating boot. So that same concept. There's a resistance to flow of current, and it slows down the resistor. So resistor is a device that slows the flow of current down. Okay. And then there are two other terms that we have to know. The second one is an inductor, which is frequently also placed in circuits. Let's put that one over here. Okay. So this is an inductor. Inductor is drawn like this. Okay, I didn't do a very good job. It's kind of like this. Okay, I remember inductors because it looks like an eye. See, yeah. It's like dot 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 dot. So that's an inductor. Now, what inductors do is, from my understanding, what inductors do is they resist rapid change in current. So the current's going, and somebody shuts off the current. I mean, like on off. That's not good. So inductors kind of go like this, slow decrease in current and slow rise in current. So they kind of smooth out the flow of current, and so they slow down and smooth out the flow of the current. So they resist changes in current. So this is an inductor. Okay, and the third term that we need to know is a capacitor, like this. Now this kind of looks like a battery, but this is a capacitor, and this is a battery symbol. Capacitor and battery, there are different symbols. So this is a capacitor. Okay, now a capacitor it holds the charge, the potential energy for a brief period of time. It's kind of like, you know, you charge your phone when it's put in the wall. You're charging like the capacitor, charging you're holding some of that energy in the phone for later use. So that's what a capacitor does. But all of these three entities, resistor and inductor and a capacitor, they're all resistance to flow in some way. This one resists and holds it. This one resists and only allows gradual changes in current, and resistor just kind of slows the current down. So all of these three entities, they resist the flow of change, and if they have a combined effect. So the total resistance to change, that's called impedance. Impedence. So that's how it's spelled, I believe. So impedance. So impedance is the total resistance to change. Okay. So it's the resistance plus the inductance, inductor, inductance, resistance, inductor, inducting, capacitor, and capacitance. C is not the symbol for capacitance. C is, like, you know, for what I know, it's the symbol for light. But we're going to be simplistic here. We're just going to call it C. So the total impedance, the total resistance to flow, as I said, all these three entities cause resistance to flow of current. It's called impedance, and it is a sum of these three. Now, it is not a regular sum; it's a vector sum. Okay, so that's what we're talking about here. They're all measured in ohms, and that's a symbol for ohms. It's kind of a terrible symbol. Okay, that's more like it. That's ohms. Okay, it's Greek letter omega. Okay, ohms. Okay, so they're all measured in ohms. Okay, so resistor, that's the symbol, kind of like mountains of resistance. Inductor, the little I over here, and capacitor over here. And these are typical components of basic circuits. Okay. Now, the impedance, therefore, the total impedance is just a sum of these three entities, but it is not like a regular sum. It is a vector sum. Okay. In other words, here's okay. Let me draw this circuit. Okay. Let's say let's say this resistor has a resistance of 5 ohms, okay, and an inductance of 3 ohms, and a capacitance of 4 ohms, okay. So the total impedance is not 5, 6, 7, 8, 9, 10, 11, 12. It's not like that, okay. So it's something slightly different. So these are drawn on an imaginary plane like this, okay. And so this is I, and this is the X. Now resistance is drawn in the X-axis, okay. So and the inductance is drawn on the positive I-axis. Kind of helps because inductance is positive on the y-axis, and the capacitance is drawn on the negative y-axis. No, negative I-axis. So when you say the impedance is sum of this, okay, so it's going to be 5. This is going to be, in this case, it's going to be 5, and the inductance will be 3I, not just 3, because it's a vector. It's in this direction, and capacitance is going to be in this negative direction. It's going to be negative 4I because it's a vector. So the total impedance, okay, it's going to be 5 plus 3I minus 4I, okay. The inductance is 3I, capacitance is 4I. So the total impedance is 5 minus 1I, okay. So the total impedance is IMPED. Total impedance is this, okay. So that's how imaginary numbers are used, because these are vector sciences. And as a review, in circuits, resistance is drawn on the x-axis, and it is a real number. So if something has a resistance of 5 ohms, it's just labeled as a resistance is 5 ohms. And inductance is drawn on the positive imaginary axis. So if something has an inductance of 3 ohms, it will be labeled as 3I. And capacitance is drawn on the negative I-axis. So something has a capacitance of 4 ohms, it will be say negative 4I. And the total impedance is a sum, is a vector sum of these three. So it would be 5 plus 3I minus 4I, again as we stated, and that is 5 minus I. Okay, total impedance, resistance to flow of current. So that's that completes our rudimentary understanding, at least my rudimentary understanding of imaginary numbers and how they're used in circuitry. So what we talked today about is how we define absolute value of an imaginary number, and it is square root of a squared plus b squared, which is the distance of the imaginary from the origin, where z being the imaginary number like this. Okay, and then we talked about how resistance, which the symbol for resistance is this, is graphed on the x-axis. The inductance, whose symbol is this, okay, it's graphed on that. On the positive y-axis, and capacitance, whose symbol is this, is graphed on the negative y-axis, and they used vector sciences to add to get the total impedance. Inshallah, next time we will do some more applications of quadratic functions and equations. Until then, assalatu wassalamu ala rasulillah wa rahmatullahi wa barakatuh. Assalamu alaikum.